Welcome back to Statistics. I'm Dr. Jeff Groh. Today we're going to talk about descriptive statistics. Remember, statistics refer to measures of a sample. Parameters refer to measures of a population. A measure of the center of a data set is a value describing the center of some data set. There are different kinds of measures of center that we often use. One of those is the mean. You'll sometimes hear this referred to as an average, but averages generally refer to measures of center beyond just the mean. So the mean, median, and mode can all be considered averages. The mean, a data set, is denoted by x bar. We put a bar over the x to indicate that we're talking about the mean. It's defined as follows. You take the sum of all the data values and you divide by how many you have added. Yes, a capital sigma. This is the capital sigma, the lowercase sigma looks like this. For some reason, sigma, a capital sigma, has come to be representative of the sum of data values. For those of you who know a little bit more, we often enumerate these data values, giving them a subscript, and we divide by how many we've added. This is the sum, as the index k ranges from 1 to n. It basically represents x1 plus x2 all the way out to xn divided by how many you've added. As an example, suppose our data set consists of 27, 22, 25, 30, and we want to find the average. What we'll do is we'll add them all up, 20, 40, 60, 70, 80, 90, 99, 104. So the sum of the data sets, this data set is 104, and there are 4 elements of this. So I'll divide by 4. 4 goes into 10 twice with a remainder of 2. 4 goes into 24 6 times. The mean is 26. There are some important things to note about the mean. First of all, it uses every data point. It doesn't ignore certain data points. It changes substantially if one data point changes substantially. So for example, suppose my data values are 2, 2, 2, and 2. Sum of the data values divided by these 4 data values. 2 plus 2 plus 2 plus 2 is 2, 4, 6, 8. 8 divided by 4, the mean is 2. What if I change one of these points by quite a lot? 2, 2, 2, and then 100. Then I have the mean as 106. divided by 4. 4 goes into 10 twice, with a remainder of 2. 4 goes into 26 6.5 times. So we changed one data point substantially. Before, the mean was 2. Now, changing one data point, the mean is 26.5. So you can change the mean substantially if one data point changes substantially. However, the mean varies less than the other measures of center that we are going to encounter. If you have ordinal data, which means you can arrange them from least to greatest, the median, it's denoted by x tilde, with a little tilde over the top, and it's actually the middle data point when the data are arranged in order from least to greatest, and the number of data points is odd. If the number of data points is even, then the median is the mean of the middle two data points. So, for example, let's suppose our data values are 1, 2, 2, 4, 21. These are arranged in order. And so 1, 2, 3, this is the third value out of 5. That's the middle. X tilde will be 2. However, if we have, say, 1, 2, 4, and 21, then we take the middle 2 and we average those to get 6 divided by 2, which is 3. Notes on the median: it does not use every data point. It only uses either the middle data point or the middle 2, depending upon whether the number of data points is odd or even. And it is not sensitive to large variations in some data points. So, for example, if my data values are 1, 2, and 300, the median is 2. Even if I change this to 3 million, it's still 2. And so large changes in these data points outside of that middle won't affect the median at all. This is one reason that median is usually used in reporting income for a nation. You'll hear this much more often than mean income or average income. The median income is not affected by the fact that some people have very, very high incomes. And so it's more likely to be representative of the middle income for a particular society or community. Another measure of center is the mode. It's the data value having the highest frequency greater than 1. If no value is repeated, or if there is no highest frequency data value, then we say that it has no mode. That data set has no mode. So let's give an example. Suppose I have 1, 2, 2, 5. Here the mode is 2, because that has the highest frequency. On the other hand, if I have 1, 2, 4, 5, this data set has no mode. It is possible to have more than one mode, in which case we say that the data is bimodal. This is bimodal or multimodal if you have several different data values with the same frequency. Another measure of center besides the usual mean, median, and mode is the mid-range. It's the mean of the largest data value and the smallest data value. So the mid-range is the maximum plus the minimum divided by 2. So for example, suppose I have 1, 2, 4, 5. The maximum is 5, the minimum is 1. So in this case, the mid-range would be 5 plus 1 divided by 2, or 3. So the note about the mid-range, it is sensitive to changes in the max or the min. So a clear example might be something like this. 1, 2, 4, let's say 21. Similar to the data value set that we just had, 1, 2, 4, 5. Now the mid-range will be 21 plus 1 divided by 2. So 22 divided by 2 is 11. So very sensitive change here. Before we had 3 was the mid-range. Now we have 11, all because we changed the maximum value to 21. There are round-off rules for these measures of center that we are going to adopt. And typically we will use 1 decimal place more than in the data. So if the data is given to, say, integers, then we'll use 1 decimal place. If the data is given to 5 decimal places, we'll use 6 decimal places. So 1 decimal place more than given in the data, but except for the mode, we'll leave the mode. Sometimes you're not actually given the data, but maybe only given a frequency distribution. For example, before we had age and these frequencies, 17 to 20, I don't know, 23, I think we had 15, 24 to, I don't know, 32, 33 to 40. We don't know exactly what the ages are necessarily. So how can we estimate the mean age of a class, say, of 19 individuals from the frequency distribution that we're given? And how we're going to do that is we're going to estimate that mean by adding up the mean of each of these categories times the frequency divided by the sum of those frequencies. If you sum of the frequencies, that gives you the total number of data points, which is typically how you calculate the mean anyway. You divide by the total number of data points. The m sub i's are the class midpoints. You'll recall that the class midpoints are calculated by taking the mean of the lower and the upper boundaries for each of your categories. So in this case, 17 plus 23 would be 40, divided by 2 would be 20. So 20 here. 24 to 32, that's 56 divided by 2. What is that? 28. And 33 plus 40 would be what? 73. 73 divided by 2. 2 goes into there, what? 30 with the remainder here. We get 36.5. So the class midpoints in this case would be 20, 28, and 36.5. We can estimate then the mean by approximately doing the following. We'll take these midpoints and we'll multiply by the frequencies. And divide by the sum of the frequencies, which was 19. We can crunch these numbers on our trusty calculators. Let's see, 20 times 15 plus 28 times 3 plus 36.5. We'll divide the whole thing by 19, and I'm getting 22.1. So for this particular class, let's say, we have a class of individuals, various ages in these various categories. We're getting a mean of approximately 22.1. Notice I'm not saying this is the actual mean of the students in the class. The best we can do here is to use the frequency distribution, since that's given to us, to estimate the class average at 22.1. If the data X has associated weights, the weighted mean is as follows. You add up the weights times the data values and you divide by the sum of the weights. By the way, this is the way in which I calculate grades. In the typical scenario, we'll have exams be, let's say, 60% of the grade. The final will be 30% of the grade, and the homework will be 10% of the grade. This adds up to 100%. And so these data values add up to 100%. The weighted mean I'll take your homework score. Let's suppose your homework score is 85%. I'll multiply that by 10. Your exam scores, let's suppose your exam scores are 92%, and I'll multiply that by 60. Your final score, let's suppose you get 99% on that. I'll multiply that by 30, and I'll divide the whole thing by 100, and that will give me your final overall weighted average for the course. In this case, let's see, I'll take 85 times 10 plus 92 times 60 plus 99 times 30. And then I'll take that and divide by 100. And this gives me about 93.4 for the overall grade in the class. Very important in this course will be measures of variation. We need some way to measure out how varied, how spread out data is. The simplest is the range. It's going to be the max minus the min. So for example, if I have a series of exam scores, suppose somebody gets a 65, that's the min, and somebody gets a 100, that's the max. The range will be 100 minus 65, so scores will be spread out over a 35% range in this particular instance. Also important are the notions of standard deviation. There's a statistic and a parameter. The sample standard deviation is denoted by S. To get the sample standard deviation, there's a big square root and a big old fraction under the square root. The denominator is easy. You divide by the number of data values minus 1. In the numerator, though, you add up the data values minus the mean squared. You add all of that up, and that ends up being the sample standard deviation. It's a statistic, and it's denoted by S. For the population, we use a parameter. The standard deviation in this case is denoted by a lowercase sigma. Remember, the uppercase sigma stood for sum. The lowercase sigma will stand for standard deviation for the population. And it's defined in a similar way. We take the sum of data values minus the mean squared, but in this case we divide by capital N, which will always denote the population size. So lowercase n represents the sample size. Capital N will represent the population size. The variance is the sample standard deviation squared, or the variance for the population would be the population standard deviation squared. That just gets rid of the square root in the computation. There is a way to use this concept of variance to come up with a simpler formula for coming up with the standard deviation, but I have to be honest with you. In almost all cases, we're going to get the calculator to calculate these standard deviations for us. I'll derive the formula for you, but keep in mind that we'll just use the calculator in the typical scenario. The variance is the sum of our data values minus the means, quantity squared, divided by n minus 1. Now, we can FOIL this out on the top. And we can separate this up into the sum of these data values squared. We're going to have this n minus 1 on the bottom still. The constants come out of a sum, and we'll have the n times the sum of these x bars. The sum of the x bars squareds end up just giving you n of the same thing, so you get n times that. Now we can simplify this a little bit because x bar is the sum of the xi's divided by how many you added. And so one way of thinking about that is that this is like n times x bar. So we're getting 1 over n minus 1 out front. We're getting the sum of the squares of the data values, and then this gives us minus twice times n times the x bar squared, plus n times the x bar squared. Negative 2 of them plus 1 of them gives you minus 1 of them, n times x bar squared. So you take the sum of the data points squared minus n times the mean squared. Multiply that by 1 over n minus 1, and that's the way to get the variance. Take the square root, and of course you get the standard deviation. One thing to note, the sample standard deviation is always bigger than or equal to 0. Yes, it can equal 0 if all the data values are exactly the same. But if they aren't all exactly the same, you'll get a positive value, but you'll never get a negative value. That's because this symbol represents the principal square root, and the principal square root is always the non-negative one. If I use that symbol with a 4 underneath, I don't get plus or minus 2. I always get positive 2. So the standard deviation defined in terms of this radical symbol means it can't be negative. So that's one thing to note. Also, S changes substantially if one data point changes substantially, is an outlier. Goes way outside of the realm of the other data points. The units of S are the same as for the data values. So if you're working in, say, a unit of length, like meters, for your data values, then the standard deviation will be in meters. If the data values are measured in feet, so you're trying to measure the heights of individuals in feet, then the standard deviation will be measured in feet. Whatever the units of the data are, the units of the standard deviation will be the same. S is a biased estimator for the population standard deviation. S is generally less than sigma, not always, but it's generally less. And now something really important to note about the standard deviation. It's called the empirical rule. And you just need to know this forever, for the rest of your life. This is really important. For distributions that are kind of bell-shaped, about 68% of the data lie within one standard deviation of the mean. That's what the standard deviation is informing us. how grouped together the data are. 68% lie within one standard deviation of the mean. About 95% lie within two standard deviations of the mean. And about 99.7% lie within three standard deviations of the mean. So almost all of the data will lie within three standard deviations this way and three standard deviations this way, within an interval of length 6 standard deviations wide. 3 from the mean this way, 3 from the mean this way. Within 2 standard deviations, 95% of the data will lie for these nice normal distributions or bell-shaped distributions. If you're using only one standard deviation, you only pick up 68%. So 68%, 95%, 99.7%. You're going to memorize these numbers. One standard deviation of the mean, 68%. 2 standard deviations of the mean, 2 this way, 2 this way. 95% of the data are going to lie in that interval 4 standard deviations wide from the centered at the mean. 3 standard deviations this way, 3 this way. 99.7% of the data will lie within that interval. This principle is called the empirical rule. We will refer to this rule very often in the remainder of the course. Because of the empirical rule, we have something called the rule of thumb. Again, the rule of thumb will only work for bell-shaped distributions. It's a way of quickly and cheaply and dirtily estimating the standard deviation. The standard deviation is approximately the range divided by 4. The range is the maximum minus the minimum, you'll recall. And if 95% of the data lie within an interval 4 standard deviations wide on bell-shaped distributions, for small samples, that's typically going to be, so all of your data, essentially. 95% is pretty close to all if you only have like 20 data points. And so the maximum minus the minimum is the range. That should cover pretty much that interval 4 standard deviations wide. Divide by 4 and that should be an estimate for the standard deviation. Keep in mind, this is just a quick and dirty estimate for the standard deviation. The standard deviation has to be calculated exactly using the method that we've written down a few minutes ago. A little bit about our variances. S squared is an unbiased estimate for the population variance. Remember, the sample standard deviation was a biased estimator for the population standard deviation, but here the population variance is an unbiased estimator for the population variance. If S was influenced by outliers, S squared will be even more strongly influenced by outliers. S squared can't be negative, and of course S squared is 0 if and only if data are constant. They're all the same value. And finally, the units of S squared are data units squared. You'll remember that the empirical rule was for bell-shaped distributions, but for arbitrary distributions, we have something called Chebyshev's theorem. And there are different ways of spelling Chebyshevs. Some of them begin with a T, believe it or not. It's hard to translate Cyrillic into English, and so sometimes the Cyrillic will give you a T, Chebyshev's theorem. But it goes like this. It's a replacement for the empirical rule when the distribution is either unknown or when the distribution is known not to be bell-shaped. The proportion or the fraction of data lying within k standard deviations of the mean is at least 1 minus 1 over k squared. And we're assuming here, of course, k is greater than or equal to 1 for purposes of this inequality. So let's see how this works out. For k equals 2, that's 1 minus 1/2 squared, 1 minus 1/4, which is 3/4, or 0.75. That means about 75% of the data lie within 2 standard deviations of the mean. Remember, for the empirical rule, it was 95%, but that only works for bell-shaped distributions. And Chebyshev's theorem doesn't say 75% will, it says at least 75% of the data will lie within 2 standard deviations. What about k equals 3? This is 1 minus 1/9, or 8/9. That's 0.888, and so on, or about 89% of the data values will lie within 3 standard deviations of the mean for arbitrary distributions. Remember, for the empirical rule, that was 99.7%, but that's only for bell-shaped distributions, or normal distributions. There's also something called the coefficient of variation. It's the sample standard deviation divided by the sample mean times 100% for samples, and for populations, the population mean is denoted by mu for the mean times 100% for the population statistic. One thing I should note is that statistics are denoted by lowercase Roman letters, whereas parameters are denoted by lowercase Greek letters. A very important concept for what comes later in the course is something called the z-score of a data point. The z-score is the difference between the data value and the mean divided by the standard deviation. And I guess that's for sample data. For population data, it's data value minus the population mean over the population standard deviation. These are your z-scores. These are unitless. What they measure is the number of standard deviations a data point is from the mean. It's positive if the data point lies to the bigger side of the mean, and negative if it's less than the mean. You can see that if x is measured in meters, then the mean will also be measured in meters, and the standard deviation will have the same units, so it too will be in meters. Meters divided by meters will have units that cancel out, and you have something that has no units at all. It's unitless. It's just the number of standard deviations from the mean that a data point has. We should also make a definition. X is unusual if the z-score has an absolute value that is greater than 2. Remember that for normal distributions, for bell-shaped distributions, 95% of the data values lie within 2 standard deviations of the mean. So if a data value is outside of that, there's only a 5% chance of that happening, which means it's kind of unusual. So a data value is officially defined to be unusual if it lies more than 2 standard deviations to the right or 2 standard deviations to the left of the mean. The percentile, not percent, but percentile of a data value X. It's denoted by, let's say, P, and it's the number of data values less than X divided by the total number of data values, and then we're going to multiply all of that times 100%. One thing to note about the percentile is that the 100 percentile is really impossible to get. If you have 100 people and this one person gets 100% and everyone else gets less on some exam, what is the percentile of that person? Well, that person is the top 100, so the number of data values less than that would be 99, and so this person would be in the 99th percentile. Even though they got 100% on the exam, they got the top score, they're still at the 99th percentile. So this is true of a lot of standardized exams. You could get into the 99th percentile, but nobody gets to be the 100th percentile. So that's the way the system works. The 25th percentile, 25% of the data lie below that value. There's the 50th percentile, 50% lie below that value. 75th percentile and 99th percentile, there is no 100th percentile. So in other words, these p-values will go between 99 and 0. It's possible to be dead bottom, in which case no one lies less than you, and so you would be at the 0th percentile if you were the dead bottom of the group. pk, this is notation. It's the kth percentile. And there are certain of these that are more important than others for various reasons. Q1 is P25, so the first quartile. Is the 25th percentile. The second quartile is the 50th percentile. The third quartile is the 75th percentile. This gives us the 5-number summary. We're going to have the minimum data value. We're going to have the first quartile. We're going to have the second quartile, which is essentially the median, because half the data lies below, half above. The fourth will be the third quartile, and then the fifth data in our 5-number summary will be the maximum. We'll have something called a box plot. It goes like this. The min occurs here. We'll have a box. In the box, the lower portion is the first quartile. The second quartile here, which is the median. the third quartile here, and then the max ends on this stem out here. So this gives you a good idea of where the data is, how the data is spread out between the entire range of the data, the minimum and the maximum values. It tells you where the quartiles lie. They could lie different distances, etc., from each other. Obviously, from the box plot, most of the data is going to be, well, half the data will be between the third and first quartile. We're going to write something called the interquartile range. Remember, the range of a data is the difference between the maximum and the minimum values. The interquartile range is going to be the difference between the third quartile and the first. So it's the distance between these endpoints on the box part of the box plot. This allows us to define another concept called an outlier. Is a data then the Q3 plus 1.5 times the interquartile range, or lower than Q1 minus 1.5 times the interquartile range. Unfortunately, it's not so easy to calculate these quartiles all the time. So there's a rule of thumb for an outlier lies more than 3 standard deviations from the mean. Remember from our empirical rule that 99.7% of the data lies within 3 standard deviations of the mean. So there's only a 0.3 chance of lying more than 3 standard deviations from the mean. Those are very, very rare. We said a data value is unusual if it's more than 2 standard deviations from the mean. Now our rule of thumb for outliers is that a data value is an outlier if it's more than 3 standard deviations of the mean. Those are rare birds indeed. 0.3% chance.
It's really important that you learn how to use a calculator or the computer in order to calculate these various statistics that we've been talking about today. I'm going to show you how to use a TI-84 in order to calculate the mean, median, the first quartile, the third quartile, the max, the min, any number of different statistics for the data. The first thing you need to know how to do is how to input statistical data. And for that, we're going to start by pushing the Stat button right here. Stat. When I push the Stat button, it opens up a menu. The menu to edit a list, to calculate statistics, or to perform tests. You will become familiar with all of these as we go through this course. So I'm just going to hit 1, and it gives me various lists. List 1, list 2, list 3, list 4, list 5, and so on that I can enter. I want to enter a list of various data points. So I'm going to enter 22, and then I'll hit enter. I'll hit 22 again. That's the next data point. So I've hit 2 22s in here. Then I'm going to type 26, 24, 23, 27, 25, 20, 24, 26, 25, 25, 19, 24, 20, 22, 24, 25, 25, 20. Yes, I'm still entering data values. 23, 30, 26, 20, 25, 28, 19, 26, 26, 23, 25, 23, 23, 23, 22, 26, 27, 23, 28, and 24. Now, if I've entered these correctly, I've entered 40 different data points. 40 data points. Some of them same, some of them different. So I've entered my list. What I want to do next is I want to calculate statistics involving that. If I want to do something else, I can just quit that. Don't worry, the data is still stored in there. In order to calculate these various statistics that we've learned about today, I need to press the Stat button again. And at this time, I don't want to edit my data, I want to calculate something. And in particular, I need to calculate one variable statistics, or one var stats. That's the command that I'll use. It gives me the option to change the list. So I just want to calculate this. And so it gives me all of those one variable statistics and some that we didn't talk about. It gives me X bar. X bar, you will recall, is the mean, the usual average, what we refer to as an average in the vernacular, but in this class, technically the mean. It gives me the sum of the X values. If I added all of those values, it would be 958. We have no reason to know that right now, but that it would be the sum. It gives me the sum of the squares of the data values. It gives me the sample standard deviation. S sub x right here is the sample standard deviation, and it is telling me that the sample standard deviation is 2.55 approximately. It also gives me the population standard deviation, which I'm not going to use here because I'm assuming that this data is from a sample. And that ends up being slightly less, 2.52 approximately. It gives me little n, which is the number of data points, in this case 40. I typed 40 different numbers in. Then it gives me the minimum x. The minimum x is 19. That was the smallest number that we entered in this list. And then it gives me the first quartile. First quartile in this case is 22.5. If I press down, it gives me more numbers to display. Beyond the first quartile, it gives me the median, which it denotes as MED here, the median, 24. The third quartile was 26, and the maximum of these x values was 30. So it gives me the entire 5-number summary here at the end. The minimum, first quartile, median, third quartile, and the maximum. It gave me a whole bunch of things in addition to that, including the mean. Remember, the median here is 24. What was the mean? 23.95. Both of those are measures of center. We could even use the average, the max, and the min to get the mid-range. 30 plus 19 would be 49. 49 divided by 2 would be what? 24.5. And so you can see the mid-range is a little bit different from the median and also a little bit different from the mean. As another illustration of the use of technology in calculating these various statistical values, these one variable statistics, Let's try a spreadsheet. So let's enter some data values here. I'll just enter 6 data values. Now I'll calculate the mean. To calculate the mean, you use the command average. And then you enter your list, and that gives you the mean. For the median, you use the command median. Go figure. And then let's suppose we want to find the min. Always begin your commands with equals, min. We'll take the minimum of the data values as opposed to the max. The commands in your spreadsheet should be fairly natural. What about the Q1, the first quartile? We'll enter the data value followed by a 1. That should give us the first quartile. Let's do the third quartile. And hence we have the third quartile. Just so you can get one more good look at that command, it automatically converted the command into capital letters. To get the third quartile, I had to enter a 3 in this location here. And that's the 5-number summary plus the mean. How about the mode? It calculates the mode as well. The most frequent entry was 22. How do we calculate the standard deviation, which will feature prominently throughout the rest of the course? The command is stdev. And for that, you need to enter the data values, and that calculates the standard deviation. In this case, a measure of spread of the data of having a value of about 2.8. So we would estimate this by rounding it off at 2.8.